Eh bien, nous avons le plaisir de recevoir au Collège de France pendant donc 4 semaines le professeur Liz-Marzán. C'est une longue histoire puisqu'en fait on l'avait invité au début, fin 2019, il devait être là début 2020. Donc il y a eu certains événements, je ne sais pas si vous êtes au courant, mais qui ont fait que tout a été décalé. Alors c'est un grand plaisir d'avoir Luis parmi nous aujourd'hui. Pour plusieurs raisons. D'abord, c'est un très bon ami, mais c'est surtout un très grand scientifique. Je vous rappelle rapidement son parcours, je ne voudrais pas être trop long. Thèse à l'université de Santiago de Compostela en 92, puis postdoc en Hollande à Utrecht, université avec Albert Philippe. Ensuite, il a été professeur invité dans pas mal de pays, aux États-Unis, en Australie, en Allemagne, au Japon, en Chine et en France, bien entendu. Ensuite, il a été professeur à l'université de Vigo, en Espagne. Vigo, c'est l'ouest de l'Espagne. Ça ressemble un petit peu, en un peu plus chaud quand même à la Bretagne, mais c'est un endroit très très beau. Donc il a été professeur entre 2006 et 2012. Et ensuite, il est devenu Ikerbasque Research Professor. Et là, c'est un système de très haute sélection en Espagne, qu'on n'a pas en France et c'est dommage. Où on a les coudées beaucoup plus franches au niveau des financements, au niveau des salaires, et on peut vraiment, je dirais, mettre un petit peu le paquet, comme on dit, au niveau de la recherche, ce qui est de plus en plus difficile en France, pour être honnête. Et donc, en fait, il a dirigé le laboratoire biomaGUNE à San Sebastián de 2013 à 2021. Et donc là, il est toujours Ikerbasque professeur dans ce laboratoire. Alors, au niveau de sa recherche, je ne vous apprendrai rien en disant que c'est un des leaders mondiaux de l'application de la chimie colloïdale à la nanoplasmonique. Beaucoup de recherches sur les systèmes métalliques. Il a été pionnier dans la synthèse colloïdale de nanoparticules métalliques avec des contributions pertinentes au niveau du contrôle de la morphologie ainsi qu'à celui de l'adaptation de la chimie de surface et de l'assemblage de nanoparticules. Ces travaux récents du groupe ont porté non seulement sur la bioconjugaison de surface, mais aussi sur l'administration de médicaments et la compréhension du devenir des nanoparticules dans les cellules vivantes. La portée des recherches de Luis ne s'est pas limitée aux aspects de synthèse chimique, mais aussi au niveau il a concrétisé ça par des caractérisations physiques au niveau morphologique et optique au plus haut niveau. Finalement, toutes ces études débouchent en fait sur un certain nombre de concepts qui peuvent être appliqués. Et en particulier, Liz-Marzán a contribué ces dernières années à la compréhension de la diffusion Raman améliorée par la surface, donc ce qui est connu sous le nom de CERS, et à la conception de substrats qui améliorent les performances des capteurs CERS pour la détection de contaminants et de biomarqueurs de maladies. Bon, vous avez tous vu l'article qu'il a publié récemment dans Science avec une chiralité sur des nanoparticules. C'était assez remarquable. Au niveau de son travail, bon, il a encadré 35 thèses, plus de 60 postdocs. Il a produit 520 articles de recherche, 9 brevets dont plusieurs licences. Ceux qui sont très intéressés par le H de bien, il a un H de 126. 250 conférences invitées dans des grands colloques, 240 séminaires, etc. Il a en fait reçu 2 ERC Advanced Grant consécutives. Au niveau des prix, il a reçu, bon, il y en a toute une série, donc je vais essayer de faire au plus court. L'Alexandre von Humboldt allemand, qui est un très haut prix. Le Dupont Prize. Il a eu des Lectureship Awards à la fois de l'ACS Nano et du Langmuir. Il a eu le prix Rhodia. Il a eu la grande médaille de la Société chimique espagnole. Il a eu la chaire Franchi, qui est en gros la médaille d'or en Belgique. Donc c'est quand même du très très haut niveau. Et au niveau espagnol, il a eu en fait le prix du roi Jaime I en recherche fondamentale. Puis plus récemment, la médaille Blaise Pascal pour les matériaux de l'Académie européenne des sciences. Et en niveau français, il a eu le prix franco-espagnol Catalan Sabati en 2020. Il est en fait membre de l'Académie des sciences espagnoles et également des 2 académies des sciences européennes. Il est fellow de la Royal Society and the Optical Society of America. Il a été également très impliqué, il l'est toujours dans les journaux, dans l'édition des journaux. Il était éditeur en chef de ACS, de plusieurs ACS journaux, comme Langmuir et Omega. Il est dans le executive board de ACS Nano. Et en fait, il participe également au reviewing des éditeurs une revue telle que Science. Voilà, je ne voudrais pas prendre plus de temps. C'est un parcours qui est tout à fait remarquable. En plus, bon, Louis a 55 ans, donc vous voyez, c'est quand même un parcours record. Je lui ai demandé, bon, je vais lui passer la parole, l'exposé bien entendu sera en anglais. Je lui ai demandé de commencer de façon progressive, parce que les auditeurs dans la salle ne sont pas tous spécialistes finalement des nanoparticules et de la nanoplasmonique en particulier. You are very welcome, Luis. Thank you for coming.
Good morning, everybody. Bonjour. I think sometimes it's good not to understand everything that is being said about oneself. After such a friendly presentation as this, I understood. We are really good friends and we like each other. But after so many things being said, the pressure now is on me. So I will have to do my best to convince you that we are doing interesting research. So as you can see in the program, I try to schedule the lectures in a way that we go from the very basic research and concepts all the way to the applications, which in a way also describes the way that I have been doing research, so the different stages along my career. And so today I will talk mainly about the basic concepts of plasmonics, and I will develop it in a way that I will try to go through concepts, to examples, and then to some more recent research that has been resulted in the discovery of new, very interesting phenomena that may still bring further surprises to us. So just as Professor Sanchez was explaining, I work at the CIC biomaGUNE, the Center for Cooperative Research in Biomaterials in San Sebastián. At the time that this lectureship was organized, I was the scientific director. Since January 1st, I'm not, but I'm still an Ikerbasque research professor leading what we call the bio-nanoplasmonics laboratory. And so I will start my first lecture trying to describe the interactions of light mainly with gold, but introducing some other metals on the way as well. And you will see the title is directly related to one of my long-lasting favorite manuscripts from the literature. So the main initial concept is the interaction of light with matter. And when we study chemistry, at least when I studied 35 years ago, we were being taught about the different areas or the different ranges within the electromagnetic spectrum, where, as you can see here, the visible range is actually a very tiny one. But it's very interesting because this is the one that we can mainly detect with our eyes. And so we are doing lots of research which is related to the interaction of visible light with matter in general. And in this context, in molecular spectroscopy, we usually focus on the ultraviolet and visible ranges. And we study electronic transitions in molecules. And in fact, if you think about, for example, aromatic compounds, there is a striking idea that if you keep increasing the number of benzene rings in these aromatic compounds, you can tune the wavelength at which light will be absorbed by these compounds. So you can somehow do molecular engineering to select the material that will interact with the light that is of your interest. And a little bit related to this concept, we have seen the birth of nanotechnology, and everybody is familiar with this. I always like to show this graph, especially when I'm in Paris. It's already a very old one, predicting many different tiny objects where nanotechnology would play a role over the years. I think that almost all of them have been fulfilled. Maybe we are not yet wearing clothing that measures our pulse and respiration, but this is very close. And all the rest, and probably more advanced than what you see here, is already present in our lives. The main concept behind all of this technology is probably this sentence. This comes from a review by Mauro Ferrari already in 2006, saying at the nanoscale there is no difference between chemistry and physics, engineering, mathematics, biology, or any subset thereof. This reflects the multidisciplinary nature of nanoscience and nanotechnology. But I would like to focus on the second part. An operational definition of nanotechnology involves three ingredients: nanoscale sizes in the device or components, the man-made nature, and especially having properties that only arise because of the nanoscopic dimensions. And this is the crucial element of nanotechnology, that we are discovering new properties of matter because of the dimensions of the material. And a very easy example related also to the previous slide is what happens in semiconductors, where, as you know, rather than discrete electronic levels, in principle we have the valence and conduction bands, which are separated by a so-called band gap, which defines the energy that is needed to bring electrons from one band to the other band. When we are in the nanoscale, then these bands start to split into either thinner bands or also already discrete levels. So it's a sort of intermediate state between the molecular level and the bulk level. And by tuning the size of the particles, you can obtain different band gaps, which lead to emission in different colors. And so this, as most of you know much better than me, this leads to plenty of materials, plenty of applications in many different technologies. Something similar happens also, I don't know why this is not working, happens also in metals. And this is again a very old slide that I borrowed from Robert Wetten many years ago. And already 25 years ago, they were publishing, Wetten and Landman mainly, were publishing about the electronic structure of metals at very small sizes and the transition between atoms and the bulk, and how you can go at intermediate sizes. You have the so-called plasmon resonances that we'll describe in more detail very soon. But if you keep decreasing the number of atoms comprising the particles, then you end up in what we now call nanoclusters, which also have discrete optical transitions and band gaps. And so actually, this field has revived tremendously during the last, I would say, 10 years or so. And now there are plenty of ways of making very well-defined clusters with a very well-defined number of atoms with very specific properties, both in absorption and emission. I will not deal with this because it's not really my field of research, but I think it's something that is really exploding at present, and there will be plenty of research being done in this respect. So I will focus mainly here in the sizes of a few hundreds of atoms and above. And of course, this brings me to this standard slide where I show the very early applications of plasmonic nanomaterials. This is the so-called Lycurgus cup. I went already a couple of times to watch it at the British Museum in London. And if you're not familiar with this, the trick is that the cup is stored in a shelf with a lamp behind, which is switched on and off intermittently. And depending on whether it's on or off, you see the cup shining green or red. depending on whether you're looking at reflected light or transmitted light. And then when the scientists at the British Museum extracted a little piece of the glass from the cup and looked in the electron microscope, they found many of these particles made of a mixture of gold and silver, which are the ones that are responsible for these different colors in transmission and reflection. Something similar happens in the stained glasses at churches. This is how Notre Dame looked many years ago. I don't know if this window is still present there. But it's also very striking, probably you all have noticed, but something I noticed very early on is that these beautiful colors can only be seen from the inside of the cathedral. And if you go out, they look mainly gray. Why is this? This is because the colors are coming from very tiny pieces of inorganic material. If it were organic material, it would have bleached already many centuries ago. So these are inorganic pigments, but they are small enough that they absorb light, but they don't scatter very strongly. And so this is the type of materials that we have been interested in for the last 30 years, feeling old. So the first scientific record that we have about this type of studies comes from Michael Faraday. Among many other honors, he was a foreign associate of the Academy of Sciences of Paris and many others. But this is the article that I referred to at the beginning of the lecture. So the title of this article is Experimental Relations of Gold and Other Metals to Light. So mine was a direct copy. But I really recommend you to read this paper. It's fully accessible online. It's a few tens of pages long. Only one very tiny equation, only one sketch, but really entertaining reading. And Faraday there is describing his work at the British institution, doing both physics and chemistry, very rudimentary. So physics was mainly related to finding ways to make metal plates as thin as possible and looking at how light would be reflected, absorbed, or transmitted through these films. And then chemistry, basically making colloids, which at that time were roughly probably not yet called colloids because Graham's work came around that time. But still, he was using different bioorganic materials to retrain the growth of gold crystals and silver crystals in water by using white phosphorus as a reducing agent. And these samples that you see here are pictures that come from the Faraday's Museum in London. So apparently, these colloids that he made 150 years ago are still stable. Somebody with probably bad intention told me that somebody comes in the morning and shakes them every day. But that, I don't know. Anyway, the colors that you see there correspond to this type of spectrum that you see here, the dotted one, while the film would have a spectrum something like this. And so if you compare, you would see that in the UV, they are very similar. This corresponds mainly to interband transitions. While in the visible and especially in the near infrared, there are very big differences between the extended film and the very small particles. And so this must be related either to changes in the structure of the metal, in the composition of the metal, or in the dimensions and the boundary conditions. And so if you extract a little bit of liquid from here and again take it to the electron microscope, and then you do high resolution electron microscopy, you will find that this is pure gold with exactly the same crystalline lattice as the bulk. So no effects coming from the composition or the crystalline structure, which brings us to effects that are related to the dimensions of the material and to something that we know now as plasmon resonances. So this would be what happens when light is shining on bulk gold or a bulk metal with free electrons in general. It can excite the oscillation of density waves within the metal, and this is what we call the bulk plasmon. And each metal will have a specific bulk plasma frequency for the oscillation of these waves. If you prepare a very thin film, then you have what's so-called surface plasmon resonance, where the density waves are localized at the interface between the metal and the dielectric. And this is actually the basis of the commercially available surface plasmon resonance biosensors, where you measure the absorption of biomaterials, biomolecules, which are specifically binding to bioreceptors at the surface. So by changing the refractive index close to the surface, the frequency of these oscillations will also change. If you now bring the dimensions down to the nanometer scale in the 3 directions, then you have what we call localized surface plasmon resonances. And the most simple way to understand this is that the electric field of the radiation will promote the separation of charges, create dipoles, and then the strength that will try to bring the electrons back to the equilibrium state will couple with the frequency of the electric field of light at a specific condition, and this will define the oscillation of electrons coupling with the wavelength of light. And this is what defines that colloidal gold looks red and colloidal silver looks yellow. Said in general, but it only corresponds to this type of colloidal gold or colloidal silver with very small spherical particles. Okay, so I will come to that also in a minute. But this is very interesting. So depending on the dielectric properties of gold and silver, the frequency at which there is coupling between the oscillation of the electric field and the oscillation of electrons in the particles will be different and will determine the color of the dispersion. Now, another very important effect that I will not discuss very much today, but will be important in the coming lectures, is that apart from this very well-defined absorption of light and scattering, and I will also explain about that, there is also another effect at the surface of the particles at which the interaction with light leads to a large enhancement of the electric field right at the surface. And this is a very local effect. The field is very much enhanced here, but decays very quickly, just a few nanometers away from the surface. And this is very important because this has also effects on the spectroscopy of molecules coming very close to the surface. And so with these concepts in mind and a few others, there has been the explosion of a field that now we call plasmonics. Probably the name was quoted in 2007 by Harry Atwater in this issue of Scientific American. But again, these historical events are always under discussion. So this is the slide that I like to show. And in any case, in 2007, there was already prediction of many applications of plasmonics in many different fields, including all that you see here, but probably I'm missing a few others. And this is why, after 30 years, I'm still working on plasmonics. I always thought perhaps I should change direction at some point. But there is always something coming up that brings my attention again to plasmonics, to either new phenomena or new applications. And so this is a very rich field of research. Okay, now back to the basics. If you want to understand how light interacts with small particles, you can go to the classic books. Boring and Hoffman is one of my favorites. And then you find these very friendly equations that describe the interaction of light with electrons and with dielectric materials and so on and so forth. Luckily, there have been very patient people like Gustav Mie who derived analytical equations. And actually, well, the previous one was also analytical, but a bit more complicated. This is a simplification that allows you to compute numerically and very quickly the extinction coefficient, which combines absorption and scattering of light, as a function of the wavelength of light, the complex dielectric constant of the material, and the electric constant of the surrounding medium, including also the radius of the particle. And this is valid for very small particles compared to the wavelength of light. Don't try to use this to calculate the interaction of light with micron-sized particles or even with 100 nanometer particles. Okay? But we can apply it for many different things. And if you use the full equation, which is something like this in the summarized version, you can also apply it to larger particles. For the determination of the real and imaginary part of the dielectric function, for metals, you can also use the Drude model, which gives you, again, analytical equations which are based on constants for different metals. And you can even apply corrections. For example, the mean free path can be reduced taking into account the particle size. And this is of application to very small particles as well. More than this, this simplification of Maxwell's equations also can be applied to concentric spheres, which was useful at the very early stages of my career as well. I'll show you in a minute. And so you can do many things with very simple calculations. This is a representation of experimentally determined dielectric functions for gold and silver compared also to the, what you calculate with Drude model, which are these dotted lines. You see that they are very similar. There are some deviations, especially in the infrared and also in the UV. But what is very important for gold and silver is that the imaginary part is always positive, but the real part is always negative in both the visible and the near infrared. And why is this important? This is important because if you look again at the equation that I just showed you, this denominator here will become 0 or very close to 0 when epsilon prime is minus twice epsilon m. So the real part of the dielectric function is minus twice the dielectric constant of the solvent. And because epsilon double prime is very small, this factor will also be very close to 0. So when this happens, there will be a maximum. And this is what determines the spectrum of small metallic spheres in the visible and near infrared. And so you see here for silver, very sharp, close to the UV. For gold, a bit more in the red, and for copper, even more in the red and less intense. So actually, if we zoom in, you will see that indeed for gold and silver, for gold, the intensity is much higher than for copper. And why is this? Why is silver more efficient than gold and copper? This is because of interband transitions, which in silver are restricted mainly to the UV part, but in gold and copper, they come into the visible and compete with this interaction of the light with the oscillation of the electrons. And this is why silver is the preferred metal if you want to do basic studies, but unfortunately, the chemical instability of silver leads to the use of gold for most applications. Okay, so any questions so far? This was very simple. Let's look a little bit at size effects. I told you that you can apply this analytical theory for a calculation of larger spheres as well. This is a comparison between experimental data and calculated spectra. In fact, because these colloidal dispersions are not perfectly monodispersed, here we did a comparison to what you calculate if you apply directly the Mie theory to the average dimension of the spheres in every sample, or if you calculate for the different populations of different sizes and then you average. As you see, the quality is probably quite good because the differences are not very big between the solid lines and the dotted lines. In any case, what you see here is that for sizes above 50 nanometers or so, you start to see a redshift and a broadening of this absorption band. And if you keep increasing the particle size, there is broadening and redshift, but also at some point you see a second band appearing. And this is because the sizes are big enough that you can accommodate higher order multiples in the oscillation of the electrons. Now, I would like to show you something a bit more advanced, meaning that we separate the calculation for absorption and scattering. And this is quite interesting in this case because you see absorption for larger sizes is restricted to the UV and the visible, while scattering is more connected to the visible infrared. meaning that in the spectra that I showed you earlier, the lower wavelength band was more corresponding to absorption, and the higher wavelength bands was more corresponding to scattering. If you talk to physicists, they will say this is not scattering, this is retardation effects. And this actually makes sense, because what happens is that when you increase particle size, the phase of the wave is not accommodating well to the oscillation of the electrons on the particle, and you see these distortions which are connected to these retardation effects as the wave is traveling through the particle. And in the larger particle, what you see, as I mentioned, for higher wavelengths, you have a very retarded or dephased dipolar interaction, but for lower wavelength, you have a quadrupolar mode, which is connected to the absorption of light. Okay, so if you keep increasing size, you would find octopolar and even higher order modes, depending on the size of the particle. Now, something that I like more than increasing particle size is changing the morphology. Before going into the morphology, sorry, I forgot about my beloved silica-coated gold. So this was probably my first high-impact piece of work related to the deposition of silicon oxide on gold spheres. And we did it in a way that we could deposit gradually silicon oxide from very thin shells all the way to very thick shells. And this was, at that time, very important. I think it's still important now. There are many people using this type of coating because silicon oxide provides protection, chemical stability, possibility of functionalization, and a few other things. Anyway, the spectra look like this. As you are increasing the thickness of the silica shell, what you see is a little shift in the position of the maximum, but in particular, a large increase in the absorbed bands at lower wavelength. And I stress absorbed bands because this is related to scattering, not to absorption. Okay? So this is mainly the Rayleigh scattering contribution of the silica shell, which is superimposing on top of the absorption of the gold cores. And the calculation done with this analytical formula that I showed you earlier coincides almost perfectly well with the experimental spectra. So you can safely apply this equation for sufficiently small particles. Now, anisotropy. Again, me theory can be adapted to ellipsoids, where you have still spherical symmetry, but you are elongating the particles. So the equation now becomes a little bit more complicated because of this summation here, but it's not very, very problematic because there are only three directions here, mainly, three axes. And so this PJ become only this PA, PB, and PC, which are called the depolarization factors and allow you to calculate the spectra, the extinction coefficient, as a function of R, which is connected to the aspect ratio of the ellipsoid, so the ratio between the length and the width. And so the calculation for different aspect ratios looks like this. There are basically two bands. It's difficult to see, but there is one band here and another much more intense at higher wavelength, which redshifts quite strongly as you increase the aspect ratio, so the elongation of the ellipse. As you increase the aspect ratio, the ratio between the length and the width. And so the more elongated, the more to the red or the near infrared you go. In fact, this we and a few others demonstrated experimentally already a long time ago by doing a very simple experiment. So first we made gold nanorods, and I will talk about synthesis next week. But trust me, we can make gold nanorods, and then we can disperse them together with polyvinyl alcohol in water. And then if you slowly evaporate the solvent, you end up with a film that you can heat up a little bit and stretch. And when you do this, you go from randomly oriented nanorods to almost perfectly aligned nanorods. And then by illuminating this film in the presence of a linear polarizer, you can see the differences in the color going through the film. So very simple demonstration. These are parallel nanorods to the polarization of light. These are perpendicular nanorods to the polarization of light. And then if you measure the spectrum without a polarizer or by measuring here, you obtain the two bands, as I mentioned. If you polarize linearly parallel, you obtain only the so-called longitudinal plasmon resonance. If you polarize perpendicular, you obtain only the transverse plasmon resonance. And in fact, if you play around with the angle of polarization, you can go all the way from one to another for two different aspect ratios, experimental spectra and calculated spectra, with a very simple combination of the angle and the polarizability parallel and perpendicular to the axis of the nanorod. Okay. Now, if you normalize now to the maximum absorption, you find something like this, and you see that for a small increase of aspect ratio of basically 2.5 to 3.5, so basically if you keep constant the thickness of the nanorods, this is only 10 nanometers increase, you find already a redshift of 100 nanometers, so extremely sensitive to the dimensions or to the anisotropy of the particles. If you now compare with experimental spectra for different aspect ratios, you see the same type of effect. You see also that this band here is more intense, which may be due to different reasons. And you also see that the width of these bands is typically larger in the experiment than in the theory, which again can be due to different reasons. The most obvious reason is that as good as we make the nanorods experimentally, it's extremely difficult to make them perfectly monodisperse. And this is why you get a mixture of ratios between the length and the width, which combined, they bring this very narrow spectra into wider ones. Another reason is that our nanorods are not ellipsoids. They are typically prisms, which can be either octagonally or pentagonally cross-section. And therefore, the interaction of light with this must be slightly different to the interaction of light with that one. And so in order to simulate or to understand this interaction of light with these objects, which are not spherical, we have to resolve Maxwell's equations. And we can do that by different numerical methods that have been developed over the year. There are quite a few. We have worked with a few of them. But since we started to collaborate with Javier García de Abajo, we mostly restricted to the boundary element method. Although nowadays you can purchase commercial software which contains several of these methods that you can apply differently depending on the problem that you want to resolve. The interesting thing is that with these methods you can basically simulate the morphology that you like to study, because you can simply draw and the method, the software will divide your material into very small pieces, calculate the interaction of light with the pieces and integrate them in a way that you obtain the interaction of light with the arbitrarily shaped object, or even with a number of objects which are close to each other. Let me show you an example of a complex object. One of the results of our synthesis has been to start with a well-defined central gold nanorod and then grow silver directly from the tips in a very elongated manner so that we can obtain very well-defined silver rods and wires up to very long dimensions. And we do it in a way that they become very monodispersed, which is reflected in the comparison between the experimental and the calculated spectra. So this would be the spectrum of the initial gold rod. And then I will show you sequentially what happens as you start increasing the length with silver. And we are directly comparing experiment with calculation. And you can see the resemblance is extremely good. And I would insist not only in the position of these bands, but also in the presence of these these lower intensity bands, which reflect the observation in an ensemble of multipolar modes. which is extremely difficult because if you start averaging out, they will quickly fade away. And so because our samples are very monodispersed, you can find in some of these long nanowire spectra, you can identify up to 9 maxima. Now, we have good friends, some of them in France, who can actually analyze these optical interactions at the single particle level. And so some of these results are coming from Mathieu Kosiak in Orsay. And so they do electron energy loss spectroscopy. So basically look at the interaction of electrons, not photons, with the nanoparticles, but there is a good correlation between these effects and the optical effects. And what they can do is to map at the single particle level, they can map the interaction of electrons of specific energies with the particles, and in this way they can localize the maximum interaction. And this can be correlated to these multimolar nodes in the optical interaction of light with the particles. And so these are experimental spectra, and these are theoretical calculations by Javier García de Abajo. In this case, containing the gold nanorod inside. In this case, what would come if we had a pure silver rod of the same dimensions. And as you can see here, when the rods are very short, there are only a few different ways of interaction of light. But if we go to much longer rods, then you can see there are many different nodes that are appearing, which correspond in energy to the maxima that we find experimentally. And so here we are correlating the bulk collective ensemble spectrum with the single particle spectrum and with the calculations from the theory, which is numerically adapted for the morphology that we have, even containing the core shell structure of these nanowires. Now, another interesting effect of the interaction of light with these metallic systems is what happens when you bring particles close to each other. And this is already an old perspective. It's already 10 years ago since we published this, where we described different effects that have been reported already at that time and some which were predicted regarding the interaction of particles and with light. And so one very popular theory that describes this interaction is the so-called plasmon bonding theory, which is something similar to what we have for molecular systems and so-called molecular orbitals. And so here we find also the way to describe the new plasmon modes that arise when particles are very close to each other by calling them bonding plasmon mode and anti-bonding plasmon mode. In some other cases, they are also called bright modes and dark modes, depending on whether you see them in the far field or only in the near field. And so there have been these bonding modes, this plasmon hybridization theory, also describing something that was called aromatic plasmons, chiral plasmons. I will also tell you more about these. And we also argued that there could be something called plasmonic polymers, which arise when you have many particles very close to each other. Anyway, if we want to model that, then we need much bigger computational power. And to do this, we started interacting with friends of ours from the University of Vigo, who are engineers working on the interaction of radar waves with airplanes and army ships and a few other things. So they basically work for the Army or for the Navy, and they use computation to calculate the interaction of radar waves with these big objects. And they use these type of machines. They apply parallel computation and plenty of computational tricks. And they participate in competitions where they sort of compete to see who can calculate like 1 million variables in the shortest time. And they showed us examples like these where they could discretize a Ferrari and then do the calculation of the interaction of different waves with this very big object. And so we argued, can we apply this exactly to our materials by reducing the wavelength of the electromagnetic radiation and the size of the objects. And indeed, soon they started calculating the spectra of nanorods, but not only of nanorods. So here they actually took our experimental morphology of the particles determined by electron tomography to make their model. And they were not happy calculating only one nanorod. They said, we can calculate almost your entire colloid. Tell us the size distribution. And so they basically randomly organize a polydispersed colloid with random orientations as they would be in the solution. And then in a single computational shot, they calculate the interaction of light with thousands of particles. And in this way, we can compare experimental and theoretical modeling so that we can obtain a more faithful reproduction of what we see in our experimental systems. And then, of course, they can calculate also interactions when particles are very close to each other. They can also apply, for example, to nanostars, one of our preferred morphologies, looking at what happens if they are coming close to each other tip to tip or tip to the central body of the nanostars. And this is actually quite important. Let me go to a more advanced calculation. So this is related to what will come probably in the second or even the third lecture, related to surface enhanced Raman. So this is one of the techniques that we use for sensing and detection. But it's very important to know where the signal is coming from. And so the signal is coming from the molecules that you want to analyze are interacting most efficiently with the plasmon resonances at the particles. And so we gave them a picture like this coming from the electron microscope, and they simulated basically the same thing and calculated the interaction of light with the full assembly of particles and calculating the hotspots at different positions, and then tell us, well, actually your signal comes from a very small number of spots in your whole sample. And the rest are either silent or have a very low interaction with the molecules. So if you want to be efficient, you should be able to bring the particles close to the tips, which we knew sort of, but it's good to know also from the theory. More important than this, if they calculate the same thing for nanostars with different densities, this was a bit disappointing. They told us if you have a lower density where the nanostars already have lots of hotspots at the tips, this is more efficient than increasing the density even if you have more nanostars, because then they will start to interact with each other and promote a sort of destructive interference that will result in a dark area here that will bring no signal. And this actually fits with our experimental data. And so if you plot this efficiency of the enhancement of the Raman signal as a function of the surface coverage for different morphologies, you find that indeed this is efficient for spheres or for nanorods. So there's a gradual increase in the signal as you increase the number of particles on the surface. And if they start to be very close to each other, then they form so-called hotspots. And then there's a sharp increase in the signal. But for nanostars, this is not efficient. So the message is you should, if possible, try to model your system before you do the experiment so that you get guidance on which way to go. All right. This is another of the predictions that we had already in 2012, that if we can make very well-defined spirals made of nanorods, we can obtain very well-defined circular dichroism in the visible and the near infrared. If I have time, I'll show you experimental data at the end of the lecture. Just the final slide about theory. My friend Javier came up a few years ago with an analytical way of resolving Maxwell's equations for arbitrary shapes. And this is a bit of a trick, because what he does is he developed this equation here to calculate the polarizability as a function of the frequency of light, including a few parameters that you see here, which are defined for different morphologies, but the parameters are extracted from numerical calculations. So the trick is once you do the calculation numerically, you extract the parameters, and then you can calculate in milliseconds the interaction of light with arbitrary morphologies. An example is this for bipyramids, as a morphology that we were studying at the time. And here, this is the comparison between the calculation with the analytical formula and what comes up from the numerical calculation. So here, this takes, I would say, hours to calculate. This one takes milliseconds. And in fact, if you're as lazy as I am, you don't even have to formulate this equation into a computational software. You can go to the nanophotonic.es webpage. There's a widget there. You input your parameters, and you will get out the spectrum and the data. So this is very simple. Javier only requests that then you cite the paper. OK. Now, more interactions of light with small particles. What happens if we use a very large intensity of light, as we have, for example, in these pulse laser systems? Then many things can happen, not very friendly for the particles typically. So, for example, you can increase dramatically the temperature of the metal by, for example, nanosecond or picosecond pulses. So in a way that you promote surface melting, and this has been widely reported that you can even induce reshaping of nanorods completely into spheres. But even more dramatically, you can also lead to Rayleigh instabilities that can end up into Coulomb explosion and really destruction of the particle into small pieces. And this has also been observed. Now, just a very brief example coming back to my 2005 paper to show you what happens if you irradiate the nanorods in these films with a nanosecond laser. And in this case, the laser was not even tuned to the maximum absorption of the nanorods. And you see here, so this was irradiation through a TEM grid. So the light would only travel through the holes. And then you would reproduce the shape of the grid on the polymer film because at the squares, the nanorods were going into spheres. So this was the change of the spectrum for two different aspect ratios. And here you see what happens if now you play again with the polarization of light. So you can completely change the contrast between the spheres and the rods, going from the longitudinal to the transverse plasmon mode, which is very similar to the spectrum of the spheres. All right, more interesting, I think. This is an effect that we found with my student Guillermo González Rubio, whom a few people here also know personally, and who was co-supervised with Andrés Guerrero Martínez, who is about to become full professor in Madrid at Complutense University. And at Complutense, they have access to a ultra-fast laser facility. And so Guillermo, during one of his stays in Madrid, was playing around with inserting gold nanorod colloids in the path of a femtosecond laser beam. And then hoping to see a controlled effect of the ultra-fast laser on the high temperature reshaping of the gold nanorods. And so at some point, he sent me a message very excited saying, so he sent me a spectrum, which he said, look at this. And I said, yes, a spectrum of nanorods, what happens? And then, he told me the full story, and I had to admit that he was sharper than me looking at the spectrum. And sharper is probably the right way for this. So starting from very high quality nanorods, with a spectrum like the red one here, he observed the transition to a spectrum like the blue one. It's not only blue shifted. Look at this, it's very, very narrow. And this is what I failed to see in the quick look at the spectrum, but he saw very easily. So let me explain why we think it's very narrow. So the blue one is what we obtained right after irradiation at the maximum of the initial nanorod dispersion. Red green is what happens after extensive purification by doing the depletion interaction separation of the longer rods and the smaller rods. But more striking, the black one is the calculation for one particle. So a little bit higher intensity, but if you look here, there is basically no difference in the thickness of the spectrum. And this, if you remember from the very beginning, this is what I said is extremely difficult to do experimentally. In fact, if you keep irradiating now at a wavelength which is a bit more blue shifted, you can also reshape these rods into shorter ones, but maintaining the very narrow thickness of this band. Another observation is that this only works if you're working at a surfactant concentration close to the critical micellar concentration. But if you work at higher concentrations, the effect of the laser is different. You obtain a bimodal absorption. And another group in Madrid, Luis McDowell, used molecular dynamic simulations to tell us that at higher surfactant concentration in solution, we are probably fully covering the surface of the nanorods, while at lower concentrations, there might be gaps that facilitate the release of heat from the rod to the solvent, so that the reshaping is probably more gradual. Another very striking effect is that this works also for bidispersed colloids. So here what we did was to mix two different dispersions of gold nanorods with different absorption maxima, so a very ugly initial spectrum, then irradiation with the femtosecond laser, and we could also take it to very narrow bands. Although here you see that there are also remaining bands at the higher wavelength, because we argue the longer rods would not easily reshape when irradiated at this wavelength. And this is the main trick. So another message here, we are not making morphologically monodispersed colloids. Here we are making optically monodispersed colloids. So the interpretation is as follows. This is a 2D plot of the absorption intensity, the absorption cross-section, as a function of the aspect ratio of the nanorod and the orientation with respect to the polarization of the laser beam. So you see there is a very narrow area where there will be a very high absorption. And this is the area where there will be enough energy injected on the nanorod so that there will be reshaping. So if the rods are either longer or shorter, they will not notice the irradiation. And this is why we can keep a band at the longer wavelength range. At the right wavelength, Monte Carlo simulations can tell us that the rod will reshape gradually, but at some point, the aspect ratio will be short enough that it will not feel anymore the irradiation with this wavelength. And so they will stop reshaping. And this is when they all become the same aspect ratio, the same optical absorption. In fact, you can also simulate, by using these Monte Carlo simulations, you can simulate the effect of different fluencies, and you see that the extent of the reshaping is different, and it compares very well to the experimental results which are up here. Okay, how much time do I have? Like 10 minutes or so? Okay, very quickly, another similar effect, related effect, again with nanoseconds on spheres. Sometimes what we see is that after irradiation of a colloid like this, we find something like that, where not only there are particles of different sizes, there are also these dark areas that if we analyze by electron tomography with atomic resolution, we can see that they correspond to holes inside of the metal. Very striking. How can we promote, by irradiating a solid metal, the formation of a bubble inside? Well, again, calculations tell us that, in principle, if you're irradiating with enough energy, you could promote the formation of cracks that may lead to the internalization of material inside of the network, which might expand. Sounds a bit crazy. We did not simulate that, but we simulated the stability of bubbles with different materials inside of a metal particle. So this is what happens with vacuum. As you increase temperature up to 1200 Kelvin or so, nothing happens. Above that temperature, the crystalline lattice collapses, and basically the vacuum is filled with metal. If you do the same thing with helium, then what you see is basically compression. So the number of atoms probably remains the same, but it gets compressed at a very high temperature. If you simulate what happens for water, what happens is apparently that the bubble will start oscillating as you increase temperature, and at some point it will want to go out. And in fact, at this selected temperature, this is what you observe also over time. We cannot observe this in situ, but at least with the nanosecond laser. But our colleagues at the University of Antwerp, the group of Professor Salavas, can do not only electron tomography, but they can also do it at increasing temperature. So they observed one of these particles with a hole inside at increasing temperature in situ, and they saw that indeed there was diffusion of the bubble to the surface, and finally formation of a solid particle. With EDX, they were able to observe that initially there was a sort of higher concentration of oxygen close to the area where the bubble is, which is not so easy to find at the end. But it seems to show that there is something inside that might correspond to water that has been incorporated during the irradiation. This is a little bit, of probably a matter of further discussion, but shows you that you can obtain very interesting and quite dramatic effects when you irradiate particles with high-intensity lasers. Something similar happens when you have core shell systems. So these were initially core shell gold-silver nanorods, which after irradiation with femtosecond laser at different fluencies, we were able to obtain this diffusion of silver to form this sort of hot dog structure, or to this ellipsoid, or in the end to spheres that seem to be completely formed of an alloy. So you can promote the conversion of a core shell nanorod all the way into a spherical alloy particle. And comparison of the spectra also coincides with the theoretical modeling. So these are experimental spectra for the initial core shell, the black one, and then the hot dog, the ellipsoid, and the spheres. And then these are simulations for the different morphologies that also coincide pretty well with what we see. So I come to the final part, which is related to plasmonic chirality. Something that has been occupying us already for a number of years, but has revived quite a lot recently. And so you all know what is chirality and why it is interesting. It is interesting because many properties of materials, of molecules, in particular biomolecules, are extremely highly dependent on chirality. One enantiomer can be beneficial for your health, the other can be a poison. And if you irradiate with circular polarized light, you can see also different absorption of light depending on one polarization or the other, which is called circular dichroism. So the question is, can we obtain chirality in plasmonic systems, and will this lead to circular dichroism in the visible or even in the near infrared? And so there has been quite a bit of work related to that, mainly related to so-called collective chiral effects. None of this is our work. This is all related to using DNA as template, either to link particles into chiral structures or to use DNA origami as templates to promote the absorption of particles into this chiral configuration, mostly helical. And these are indeed experimental spectra coming from this type of organized molecules with DNA. Together with Andrés Guerrero Martinez, whom I already mentioned, some time ago, already more than 10 years ago, we looked at the theory that was developed by Sasha Goborov regarding the organization of gold spheres into helical arrays, where you could see that if you have 2 spheres or even 3 spheres, it's impossible to get a chiral structure. But if you have a 4th sphere, like here, then you already have something that looks chiral, and then you can obtain circular dichroism, as I said, indivisible. And then if you increase the number of spheres, the sign can change. The wavelength doesn't seem to change very much because it's mainly connected to the plasmon of the single sphere. Together with Baptiste Auguier, who was a postdoc in my lab, he's now a lecturer in New Zealand, we basically adapted this theory, the so-called coupled dipole model, to ellipsoids. And for ellipsoids, it's striking to see that already 2 of them placed in a sort of chiral configuration, so different plane and different orientation, they already can display circular dichroism. And this is what we used to explain what we observed for these, I would say now, very ugly arrays of nanoparticles using helical polymer materials as a template. So this is what we obtained for spheres mixed with these helical fibers. And this is what we obtained for nanorods with helical fibers. In none of these cases, you would say we have a helical array of nanoparticles. However, although for nanospheres we do not see any signal, the dotted lines here, only the signals corresponding to the organic material itself, for nanorods we see very well-defined spectra, both enantiomers, depending on which chiral structure we were using to the right or to the left. And this was actually very hard to understand until we noticed that if we have combinations of pairs of nanorods, which are all going into the same configuration, the sum of the contributions of the different pairs will come up into this very strong circular dichroism signal. We then did also work together with Stefan Link and Peter Nordlander to analyze at the single particle level. Again, coming to the 2 nanorod model, where for single gold nanorods, in this case, sort of dog bone structures, you see very well-defined plasmon resonance, but you don't see any circular dichroism. And then we were able to encapsulate pairs of these nano dog bones in solution by using a polymer encapsulation. And then again, if you measure in dispersion, you see some changes in the optical absorption because of the plasmon coupling, but again, 0 CD in the bulk. By doing single pair spectroscopy, Stefan was very disappointed to see the extinction, in this case scattering band from the pair of rods, but a signal in CD that was comparable to the noise. And in fact, if you calculate for parallel dog bones, this is really what you get, 0 CD. However, in some cases, the nanorods were not parallelly oriented, and then you can obtain experimentally something that looks very much like the theoretical prediction. So indeed, 2 nanorods which are misoriented can lead to circular dichroism. I will tell you more about this because it has biosensing consequences. But just for today, we were also able to make these much better organized helical arrays of nanorods, which display circular dichroism something like this, which is very similar to what we calculate for polydispersed helical arrays of nanorods. So this will come probably in the 3rd lecture. Now, more challenging was to make single particle chiral plasmonics. And the first really nice report came from the group of Kita and Nam at Seoul National University. I can say now I was a referee for this paper. And at the time I was refereeing and showing to two of my postdocs, Guillermo and Jesus, they said, but we are doing that. And it was not exactly the same thing. I'll show you in a minute. But it was a bit of, pushing them a bit harder. That they had to come up very quickly. But this is a very nice piece of work. So they developed a process in which, starting from gold octahedrons or even gold cubes, and using chiral amino acids as surface modifiers, they were able to promote the CD growth into these intricate, they call helicoid structures. And they obtain very strong circular dichroism coming from these particles, and by preparing thin films with these particles, they actually were able to create circular polarizers from this type of materials. Anyway, what we did was a bit different, and it worked, and I will tell you more about the synthesis next week. Let me just show you some examples today. So these are some examples of our helical gold nanorods that result into very well-defined circular dichroism in the visible and the near infrared. And with this spectra, what I show you is that we can also make the two enantiomers depending on the synthesis strategy. And in fact, if you compare the optical spectra, the optical CD, with the calculations, you also see that by changing the morphology, in this case, the extent of the grooves that form the helical structure, you can take the CD all the way into the into the mid-infrared, so to say. And as you can see here, the anisotropy factors are also very high, close to 20% for these materials. Honestly, I should say routinely we can get 10%. In some good cases, we can get close to 20%. We are now working on trying to optimize the preparation of these materials. So with this, I will finish today. But of course, this is not the full story. I could have been continuing talking about the interaction of light with different arrays of materials, like self-assembled superlattices, metamaterials, and many other plasmonic materials. But, well, some of them I will discuss in other lectures. For the moment, I would like to thank you very much for your attention, collaborators and funding agencies, and I'll see you again next week. But I'll be happy to answer questions today.